Hello, my name is Scott Berry, and I'm a biostatistician with Berry Consultants, and I'm going to show you today two distinct topics, meld them together, and show you how each one through time has paralleled each other. The NCAA football, where we have 120 plus teams, and we're trying to find what's the best team. And the recent Ebola pandemic, where we have many treatments we believe may be effective in this pandemic, but how do we figure that out? How do we set it up? So two distinct topics, we'll bring them together, and I'll describe the interesting statistical parts about both of these. So college football, some of you may know the setup of this. It's gone through three transitions, and I'll explain to you how these transitions actually mirror clinical trial development. I know two things that don't seem to be connected yet, but I'll try to connect them together. So before 1998, what happened in the world of college football were that every team had a set schedule, think fixed trial, where they had to play a certain set of teams. It was determined many years ahead of time. We had to have a protocol for how it worked. And at the end of the season, each teams were grouped up into leagues. The winner of that league would play the winner of a different league in a bowl game. And that was scheduled years ahead of time. At the end of this, we had to declare a single winner of the college football season. Now, the bad part about this was because it was predetermined everybody who they played throughout the course of the season, you'd end up with a structure like this, where the number 1 team might play the number 7 team. The number 2 team plays the number 5 team. Maybe they both win. And at that point, now you have to decide who's the champion. There is no championship game. It's a vote. Think of a DSMB, perhaps. The committee deciding who's the winner of this season. And at the end of that, their decision is a lot like the world of clinical trials. We develop a drug, and we notice that this drug works well against this control, and this drug beat that control. They both won that game, but who's better between these two? We have to make those decisions, and we never get to see them play each other. This is the world of college football pre-1998. This is the world of drug development now. So what happened in 1998 was that college football developed what's called the Bowl Championship Series. This is where they play the same fixed schedule throughout the season, but the very last bowl game is now determined by a vote of a committee. So the committee decides this is the best team, this is the second best team, let's put them in a game together. And that's what's done through 2013. So this is much better in at least we have a fixed trial set up through the end of the season, and then the two best teams, or thought to be two best teams, again, in a way that they don't even necessarily play common opponents. They played a team who played a team who played this other team. We decide who we think's best, and those two teams play each other. And the winner of that single game is now the champion. This is an innovation in the way the schedule is set up. This is an innovation in the science of college football in setting up who is the champion at the end of the year. Now, in 2014, things changed. They decided that two teams playing in one final game is not enough for us to know the single best team at the end of the year. So what they decided is we need 4 teams. So they play the same rigid, fixed schedule, and at the end of that, the committee, the Data Safety Monitoring Board, decides these are the 4 best teams. I want 1 to play 4, 2 to play 3, and the winner of those 2 play. So we're getting much better at figuring out, and think of a football game as a clinical trial, who's the best treatment, who's the best team at the end of the season. What's really neat is here's a graph from Sports Illustrated, and in the graph they show what would have happened had this system been in place last season. They show the teams that were ranked early on as being good, and then you see some teams, Michigan State coming in late, Auburn coming in late, that they jump up, and boy, these teams look really good. They jump up in the rankings, and they would have been in the top 4 at the end of the season. This graph looks a lot like some of the graphs I'll show you in an Ebola trial. And naturally, they simulate their trial What would happen had we done this last season? This is what we do as scientists setting up clinical trials. So you'll see this graph again, hence the connection to the Ebola epidemic. So the Ebola epidemic, an outbreak in Africa, the disease spreads, thousands to projections of millions being infected, and we have no drugs. We have a lot of possible therapies here. It's like a college football season, 120 plus teams starting out the season. Which one is the best of these? We have to figure that out incredibly quickly. Patients dying at the same time, very much a critical situation. So there are a lot of different groups of subjects who have Ebola. There are those that have low risk of it. Maybe they're aid workers. They may become exposed. Think of a 1% risk. Then there are those that bring a family member that they've been caring for directly to a hospital. These are subjects, they test them, they're seronegative, but they're very high risk of developing Ebola because of direct exposure. 40% risk, perhaps, of developing Ebola. Then there are those that test positive but are non-symptomatic. And you see that in red in this situation. Those are the subjects I'm going to talk about at trial. Interestingly, you could perhaps run a trial with multiple groups at one time. Then there are those that are positive and symptomatic, the disease has progressed. We're going to look at those that are test positive but essentially non-symptomatic. They may have fever as the first symptom. There are many possible treatments. We have many antivirals that may work, projected to work. We have other therapies that have been developed in the lab that show a promise against Ebola, perhaps even combined with an antiviral. We have convalescent plasma. This is where you give plasma from an individual who has recovered from Ebola. And the idea is they have defenses against Ebola and that you can transplant this plasma in them. So a wide range of therapies that might work, somewhat like an NCAA football situation. We cannot give placebo in this population. It's not believed to be ethical. Okay, so what is the strategy? The typical drug development strategy might be the following, where we explore a sequence of single-arm trials. We can't give placebo. In a way, it would be nice if we could do drug 1 against placebo, drug 2 against placebo, and then when drug 3 and 4 come about, we compare them to placebo. Now, this is like a sports contest where everybody has a common opponent, and we see how much does 1 beat placebo, how much does 2 beat placebo, and we pick out those with the largest differences as being the best team in that situation. This is a tough situation. Now what we have is you have a single-arm trial of drug 1. The population is different, the severity is different, the protocol is different when drug 2 is a single-arm trial. This is like a sports competition where you watch a scrimmage, where it's raining in one situation, it's cold in another. There's variability, there's heterogeneity. Now we have to pick a winner after watching 4-team scrimmage. Very, very difficult to do. The science of how we've set it up has put the decision of what to do with millions of patients in a very tough situation. So then the committee has to pick this winner in this scrimmage. What would be better? Well, what would be better is if we could have these common components, or essentially they play together. Imagine now that you've seen these 4 teams in this scrimmage, and now you have to ask the question, well, what if we combine 2 and 3 together? What would happen there? Well, we haven't even seen them scrimmage. That would be extremely difficult. So what is our approach? Our approach is let's throw them all into a common arena. Let's put 1, 2, 3, and 4, and if 5 isn't ready, let's start the game, and when 5 comes ready, it can jump into the game at the middle of the time period. We want to do better than having 1 and 2 play a game and 3 and 4 play a game and the 2 of them come together. We want them all to play in the game at the exact same time. Can't do this in football. We don't have 4 end zones, but we're going to throw 4 therapies all in there simultaneously, and if 5 becomes available, we put it in there. We can do more than that even, because we can say, you know what, 1 looks really good, 2 looks really good. Let's take their best players, put them together, and see how well that does. So we can combine them together and look at regimens in a common arena. Okay, so I'm going to show you an example of what this looks like. Think 4 active agents starting out. And again, we can add a 5th, 6th as the trial goes on. We have single agents, 1, 2, 3, and 4. We can combine them together to make a double regimen, 1 and 2 together, 2 and 3 together, and so on. This creates 10 treatment arms. In the graph here, you see that there are 4 single agent arms in green, and there's another 6 doublets or regimens that we can use. 1 and 2 can be combined together, for example. So we have 10 treatment arms starting out in the trial. We are going to have an endpoint here. Think mortality, 14-day mortality perhaps. We're going to have a definition of what is failure in the trial. We're going to start, we don't have any data yet, we're going to start the trial on each of the regimens, 10 regimens, 3 subjects on each for the first 30 subjects. At that time, we're then every week, we are going to update a randomization and decide, you know what, this regimen looks good, this regimen looks good, give that more often. I want to see those 2 teams play. Imagine if the committee could change the schedule throughout the season to match up the best teams. We have a much better chance of picking the best team when the season's over. That's what we're doing in this trial. We're going to do response adaptive randomization. Every week this gets updated. We have a 20-patient delay in information. So when we do an update, there's 20 patients delayed, and then we go a week later, this is going to continually update. And I'll show you an example of what this looks like, adjusting for the information. This trial goes on as long as I need to decide who's the best team, which is different than a football game lasts 60 minutes. This is going to go perpetually until the Ebola epidemic is over, or we've decided this is the best team. Everybody should be treated with this. Okay, so the statistical model we're going to use is one where we have a grand mean alpha. This is on the Logit scale. We are going to have a factor for each individual agent that's in the trial, the active agents. There are 4 of those. And then we add in the interaction term for adding 2 agents together, an X, Y combined together. Those were the 6 extra regimens. We have a coefficient for each one of those. We have prior distributions on each of the main effects, the X's, and we have a prior distribution on the individual interactions. There would be a process, of course, of deciding what these are, but we're going to start with a prior opinion of 0 benefit, 0 interaction between 2 of them with a standard deviation of 1. We could make that smaller or larger depending on the expectation of interactions between 2 therapies. So this is the statistical model that's going to drive the clinical trial. So here's an example. I'm going to run you through an example trial here. What you're going to see, and there's a movie of this, and so I'll start very slow and then we'll pick it up as we go through this. On the left-hand panel here, you'll see the new data that comes in the last week. And this is going to be 10 patients every update with a lag of 20. You see a gray one here means the subject was a success after 14 days. A red dot means the subject was a failure. So at this point we have 2 failures. Therapy 2 right now is not looking as good. We have 2 failures on that therapy. The middle plot shows you the cumulative data as the trial goes on. So the left is the new data, the middle is the combined data throughout the whole course of the trial, and it shows you the percent of failures in red in the middle graph. The far right is just the statistical model. The red bar for each of the treatments is the posterior median probability of a failure for those treatments. So initially you can see the median for the 2 arms that had a failure is quite high, estimated 40 to 50% probability of failure on those arms. The other arms are doing better. The red shading going in the vertical space is the 95% credible interval for each one of those treatments. Again, we're very early, very, very wide bars to that. The green dot is the probability that that arm, that regimen, is the best regimen of all 10. They each sum to 1 in this situation. So we have a probability of a best team, and that's going to evolve as the data evolves. We're going to use that for the randomization probability in the next period of time. So think of the green dots as the new randomization probabilities. We've updated them a little bit for information. So if one arm has more patients, we're going to favor the other arm to increase our information. The blue dots show you the probability that that individual factor, they're only for the 4 individual factors, is in the best regimen. So it could be that if 3, 4 is the best regimen, the probability that 3 and 4 are in the best regimen are both going to go up and going to be high. So here's the first update. We create new randomization probabilities. We randomize the 10 patients in that week using those new randomization probabilities. And we get a new set of data. We move to the next set. We get new data here on the left. The middle is the cumulative data. And the far right is the statistical model based on the data that's now asking for patients. And as you can see in this situation, it likes 4. It really likes 4, and it kind of likes therapy 1. And so it likes 1 and 4 together. It likes 4. And at this situation, 3, 4 is looking pretty good, though 3 by itself doesn't look as good. So the trial walks through, and I'll walk you through several updates. And you can see about this point in the movie, we really start to like the 1 versus 4. We don't like 1 by itself. We don't like 2. So we give very low randomization probabilities. If at all, I don't need to see 2 play anymore. I know they're not as good as 1 and 4 in this situation. So we're going to ask for more and more competitions of those. So now we're really liking 4. We're going to ask for more of those. 3, 4 is looking really good at this situation. The trial continues on, and you can see in the left panel the data coming in is really heavily on 4 and a little bit on 1 and 4. At this point, we're really starting to like, we're now at 200 patients. We really like 3, 4 together. You can see in the statistical model, the estimate is less than 10% failures relative to 40 and 50 on some other arms. We see a very high probability of 90+% that that's the best regimen. The probability that 3 and 4 are in there is very high. 4, for example, we know 4 has to be a part of the regimen given. We run this out, and again, I talked about this being perpetual, so I run it out to 250 patients. You can see in this situation we have about 100 patients out of the 250 that were given 3 plus 4. We got a great deal of information on that. We saw 4. We saw 1 and 4 together quite a bit as well. Any regimen with 4 in it got a lot. This is a final summary of that trial, and notice the left-hand graph looks a lot like the Sports Illustrated graph I showed you, where this shows the randomization probability from starting 0 all the way through 250 patients. You can see the 3-4 arm started off low, and about halfway through the trial it really shot up as we were starting to become convinced that that was the best regimen. And you can see each of the randomization, each regimen is a color. When the 2 colors mix together, that's the regimen combined with the other regimen. The 2 agents combined to form a regimen. The blue and green are the 3-4 together, and you can see at the end of the trial at a very high randomization. Interestingly, since I know the truth about the scenario I simulated, the yellow bar here is the probability that a subject is going to fail given the randomization at the particular time period. So if we go in one slice of time, that shows the probability that a subject fails or dies in the trial. You can see when we start off equally likely, we're up near 30%. As the trial goes, we learn better and better treatments. We're treating the patients better. That probability comes down near 10% is the true probability of failure in the trial when we get to 250. So we would end this trial, 3-4 would be the winner of this. the champion of the season would be the winner. We could bring other therapies in at this point. The trial can continue. So that's an example trial. Now let me show you what happens if we simulate 5,000 trials just like that in some different scenarios. We can investigate how well does this approach work. We could go, for example, and say how well does the BCS work at getting the best team. Lots of papers were actually written on that. In this situation, let me jump ahead a couple slides to scenario 3. This is actually the truth of the scenario I showed you one trial from. That last trial, this is the truth from that. The blue is the probability of failure in each of the squares. The probability is 20% 4 by itself, 30% 3 by itself, 40 for 1 and 2. 3 and 4 work, 4 works better. You can see when we combine 3 and 4 together, the probability of failure is 10%. It's the single best regimen. That's the scenario. I get to create the scenario 3. That's the truth in that situation. The result of the simulation is the average sample size is shown as this glob of red and green points in the middle. The red ones were successes, the red ones were failures, the green ones were successes, and so you can see the average number of those. You can really see that the trial on average puts 89 patients on the 3+4, and at the same time an average of only 6 or 8 patients, 6 to 8 patients on 1 and 2. We very quickly learn it doesn't work. Hence, we put many more subjects on 4 and 3-4, at that point we have a much better probability of determining the best treatment because we don't waste patients on therapies that don't work. The probability of selecting each agent as the winner at the end of the season is the black probability at the bottom of that regimen. In the 3-4 square, that's 89% of the trials. We said 3+4 is the best when we reach 250 patients. In parentheses is the probability if we had to play a fixed season. We had to give every therapy the same probability. We use the combinations, but we have to give it the same probability. That's about 81%. So in this sequence, we have an 89% chance with the adaptive randomization. We have 81% in fixed randomization. The number of failures in the trial, if we do this adaptive, is an average of 49 out of 250 patients, where if we do fixed randomization, it's an average of 70 in that situation. So this process has a higher rate of success, almost a 10% increase in the probability of successes, and it increases the probability of getting the right answer when the trial's over. We've looked at 8 different scenarios here. I'm backing up a little bit now. Here's the null scenario where you can see in general we search over all 10. They get very equal number of patients and equal probability. Each one is considered the best at the end of the day. We're really searching for something that works. They all have exactly the same probability of success. So this trial works just like a fixed trial because that's good for this scenario. Scenario 1, therapy 4, as long as you put 4 in the trial, it works very well. The other therapies work at 40% failure rates. Therapy 4 has a 20% failure rate. You can see we end up putting a very large proportion of the patients on regimen 4 with high probability of selecting it. Again, about 20 less failures out of 250 patients by doing the adaptations. I showed you scenario 3. There was a unique best answer of 3+4. Scenario 4 is also the best answer. And here, what's interesting is therapy 1 is detrimental. So in this case, if you give 1, it has a 50% failure rate, even if you give it with 4. And you can see what's really nice about this, not only do we favor the good ones, we get away from ones that harm very, very quickly and we never select them. Here, again, we have about a 40 patient increase in the number of successes because we learn what doesn't work very quickly in this scenario. Okay, so, and this is the beauty of this, is before this season starts, before the trial starts, I can simulate any scenario and make sure my process has a high probability of getting the right answer, and at the same time does it in a very efficient manner. It's an arena, we can throw all the therapies together at the same time. Scenario 6. Scenario 7, again, there's very strong harm here, creating a very large discrepancy in the success rates. So, we connected two topics you might not think have a very similar science to them. The NCAA has to be smart about selecting the best team. Of course, they're worried about money, which, by the way, clinical trials sometimes are worried about money, so they parallel in that way as well. The NCAA has gotten better and smarter, and we can even simulate what would have happened in seasons before this year. Clinical trials are doing the same thing. We're getting a common arena, throw them together, let's make them play early and often. We can be much more efficient about getting the right answer, and in the process we do efficiently with time and the patients we ask to be in our clinical trials. So thank you.